Dear students, today our topic is angular magnification and simple microscope. Okay, this is going to be a very simple topic if you have already studied the previous topics about lens and the lens equations. So this is kind of pretty simple thing. Okay, the angular size of the final image produced divided by the reference angular size gives us the ratio which is commonly known as the angular magnification. Okay, so to define angular magnification, we need the angle by which the final image is made divided by the angle by which the image was seen without the magnifier. All right, so the angular size of the final image produced, angular size or theta, or the angle by which the image was made, is called the angular size. All right, so the angular size of the final image produced divided by the reference angular size. What is the reference angular size? It is the angle by which the actual image can be seen. All right, so this is the reference angular size here. Gives us the ratio which is commonly known as the angular magnification. This ratio is called angular magnification, and mathematically we can write it as this thing. Okay, so we just call it as equation number 1 here. So we've defined angular magnification. Now we need to just come up with a definition of simple microscope. What exactly is a simple microscope? You might think of a compound microscope when you just read this word out loud. All right, so this is not a microscope that is used for, that in biology lab and all that. This is just a simple microscope. So what is a simple microscope? A simple microscope is a magnifying glass that has a double convex lens with a short focal length. So a simple microscope is nothing but just a magnifying glass. All right, it just doesn't look like a magnifying glass. No, it does. Okay, this is a magnifying glass. All right, and it is also known as a simple microscope. Okay, because it just magnifies things. Okay. So now, how does a magnifying glass works? How does it magnifies the image, the angular size of an object? All right, so first we need to draw some diagrams over here. Okay, so in the case, if we look at the object right straight through our eyes, okay, if there is no lens in front of our eye and we look at the object just straight directly, all right, such that the object is placed at a distance which is the near point of the eye, which is around 25 centimeter. If you just place any object at the distance around equal to 25 centimeters, then this is the nearest point at which the image is seen clearly. All right, so we have taken this as a reference point. So now if an eye sees an object which is at the distance equal to the near point, then the angle made by the eye to a point on an object, we consider this point. We don't take this whole arrow, we just take this point right over here. Okay, so the light which falls directly on this object, all right, makes an angle theta with the perpendicular axis, and this theta is known as the reference angular size, all right, or simply theta. This is the angle by which image can be seen directly without a magnifying glass. Okay, but what happens if we put a magnifying glass, or simply we can say a convex lens over here, right? If we just place a convex lens over here, the image was placed at a distance about the near point of the eye, but here we are gonna place this this object at around halfway between the lens and the near point. All right, near point is this n distance from the eye, and object is halfway between this near point and the length. All right. Now what happens? What happens is this: we have to trace the ray diagrams of this object in the case of lens. So first we are gonna take this A ray. A ray just travels perpendicularly parallel to the principal axis and then gets passed through the focus. Let's say if this was the focus, okay, so this was the focus, it would just pass through this like this. All right. Okay, if it just passes through the focus after getting parallel to the principal axis and striking the lens, of course, this was the A ray. And the what is a C ray or the O ray? The O ray passes right through the center and just continues to travel without any refraction. So this is just a C O ray that just travel along a straight line and without getting refracted, of course. But here, how would we get our final image? We know that in the case of convex lens, we have to redraw it. You might have think that in case of convex lens, we don't have to redraw things. We will get the image over here. But when the object is placed between F and O, then we will get a virtual image, a larger, a magnifying image. Okay, so the cases you have studied about the convex lens is that the object is placed beyond F. Okay, if it's placed beyond F, then we will get a magnified, but you can say a real image, all right, an inverted image. But if this object is placed between F and O, then you will get a virtual image. In case of lens, a virtual image is the one which is made on the same side of the lens as that of the object. All right. Okay, so we will have to redraw these lines to meet at a point, and this point is where the image will be formed. The intersection point is the point where the image would be formed. All right, so this image you can clearly see that is much larger than that of the actual object. Okay, so this is a pretty simple thing. Now coming to the calculation. For calculation, I have placed this eye right over here so that you can understand what theta dash is. All right, theta dash is the angle at which the image of the object is subtended. All right, so this is only for your clarification of concepts. But when we're going to do the calculations, we are gonna take this eye over here, we're gonna bring this eye over here like this, and we are gonna place it over here. All right, I'm really bad at drawing. Okay, this is the eye. Okay, we have just brought it right very close to the center. Okay, why did we do this? We did this because we want this angle to get equal to this angle. Okay, when I was here, this was the final angle, all right, the theta dash. When I was here, the eye was brought here, then this would become the theta dash. All right, so that we can use this triangle for our calculation. We've brought it closer to our center of the lens so that we can calculate this triangle for, you know, just calculation of this angular magnification, of course. So now we are gonna use these two diagrams to get two kinds of tan thetas. All right, in the case of naked eye, right, where there was no lens, we can use tan theta, of course, again for this triangle. Okay, so tan theta here would be equal to perpendicular by base. So perpendicular in this case becomes HO and base becomes, of course, N. Okay, so perpendicular is HO and base becomes N. Okay, so we just call this equation as number 2. Next, we're gonna use this image, and from this image we are gonna just use this triangle. Okay, this one. That is why we have brought this eye so close that it just starts seeing at this point, and the angle it makes is given by this theta dash, right? So we're gonna just solve this triangle by tan theta dash. So tan theta dash becomes perpendicular by base. Perpendicular in this case becomes HO divided by what is base in this case, okay? The base is the distance of the observer to the object, okay? The distance of object to the center, DO, and distance of object to the observer are the same. That is why we have placed this I over here, okay? So I is placed at O. So the distance between the object and O is the same as the distance between the object and the I, okay? So in this case, this line is equal to DO. Okay, so base becomes DO, right? So we've got these two equations. In the previous cases, we had tan theta equal to tan theta, but we don't have tan theta here. We have different angles. We don't have same angle here. We have a tan theta and we have a tan theta dash. These are two different kind of angles. You can see this is much kind of small angle as compared to this one. How are they gonna be equal to one another? How are we gonna solve this? So we are gonna use some mathematics over here, okay? So if theta is very small, then this is the property of used in mathematics, that if theta is very small, then tan theta becomes theta and tan theta dash becomes theta dash, okay? It doesn't mean these two are equal. It just means that the tangent of this angle is equal to the angle itself, and the tangent of this angle is equal to the angle itself, the theta dash itself. All right, this is the property we use in mathematics in many cases, right? You might have studied it in your mathematics course. Okay, so if theta is very small, then tan theta equals to theta and tan theta dash equals to theta dash. All right, so we have considered the case of very small thetas, right? So that these thetas are equal to their tangents. Now what are we gonna do? After this point, we have already obtained theta and theta dash. So we're just gonna use these two things over our equation number 1. Alright? So m theta, which is the angular magnification, equals to theta dash divided by theta. So we're gonna use HO divided by N in place of theta dash here, theta here, and the thing HO divided by TO over here. So nothing difficult over here. We're just gonna cut these things off. HO would cut off HO over here. Okay, so we're left with 1 by TO divided by 1 by N. So we are gonna just simplify this one. Okay, 1 by TO divided by 1 by N, just like this. 1 by DO divided by 1 by N and 1 by DO divided by 1 by N. We've just write it like this so that we can just simplify it further. Right? So it is a property of mathematics again that if these two quantities are getting divided over here like this, and if we just invert one of these values, we can replace the divide sign by multiply sign. Okay, so we're just gonna convert this divide into multiply by inverting this value. Okay, so 1 by n's become n by 1, so divide becomes multiply, so it becomes n into 1 and do into 1 equals to do. This is our fourth equation. All right, so now what are we gonna do? We are gonna use the length equation. The length equation says 1 by f equals to 1 by do plus 1 by di. All right, so here we need 1 by do because in equation number 4 we have 1 n into 1 by do. Right, so evaluating 1 by do, we get 1 by do equals to f minus di from this equation. Alright, so we're gonna just use this 1 by do, the equation number 5, 1 by do over here. Alright, so using equation number 5 in 4, we get m theta equals to n, the remaining part 1 by do, but instead of 1 by do we are using its value 1 by f minus 1 by di. Now we call this equation number a, and this is the required formula for the angular magnification. Right, this is the formula that we use to get the amount of angle, okay, the ratio of magnified angle to the you can say the reference angle, which gives us the ratio of magnification. But we are not done yet. Alright, we are just gonna see two cases which are important, because we don't know what happens if the image is created here or way beyond this, right? Or if the object is placed here or way beyond this. Okay, we have not considered this case yet. So coming to our cases, case number 1 is that in the equation a, if di equals to minus n, what is minus n? Right, the closest distance of image from which it can be seen clearly is the near point of the eye. We already know that. Hence, we will put di equals to minus n over here, okay? Because we want to just measure the amount of magnification for the closest object to the eye, right? So, for the closest object to the eye, what is the distance closest to the eye? Of course, it's near point. Alright, so n is the near point, and negative sign shows that the image is at the same side as that of the object. So it is to the left side of the object. Alright, the eye is at the right side and the image is at the left side. That is why we have used the negative sign over here, right? So putting di equals to minus n over here, we get, using di equals to minus n in the equation number a. Okay, so we're going to use minus n in place of di. We get this thing, we're just minus gets plus. Okay, so we're going to multiply this over here. We're going to multiply this n over into the terms inside the brackets. So it becomes n over f plus n over n, and then gonna cancel each other. N by f plus 1 is our final answer in the case when the object is placed very near to the eye. Case number 2, when the image is made at a distance infinity, right? Distance of images at infinity. The far point of eye is infinity because normal human eye can see objects that are infinite distance apart. Of course, we can see things which are infinite distance apart, like the stars, the sun, and many more terrestrial objects, as long as the light reaches us at the proper angle, of course. Okay, so using di equals to infinity in equation A. Okay, so m theta equals to n into 1 by f minus, we are going to use infinity in place of this di. Alright, so 1 by infinity gives us 0. So we're just going to skip this 1, because 1 by f minus 0 of course becomes 1 by f again. So we're going to just multiply this n to this 1. So it becomes n over f minus 0, of course. So we're going to just drop this 0 off. And the final equation becomes n by f in case if the image is made at infinite distance apart from the eye. Alright, so these two were the cases where the image was formed very near to the eye and where the image was formed very far away from the eye. Right, these are the two cases of the angular magnification using a simple microscope. Right, thank you so much, everyone.